Hello, everyone. It's me, Mr. Younger, again, teaching my conceptual physics class. And of course, we are using the 13th edition of Hewitt's Conceptual Physics. But this is non copyrighted material, and I'm just trying to further explain how we add vectors, which was a topic brought up in chapter 2 and of course later chapters as well. But chapter 2 is where it's first introduced in Hewitt's book. So let me go ahead and share my iPad screen with you guys so you can follow what I'm talking about and you can see my writing and drawings. So let's begin. So this particular uh, presentation is geared at answering the following questions so that we can sort of understand what vectors are, how they're added, and that sort of stuff, as well as knowing what are some examples of vectors and so on and so forth. So we first off ask the question, what is a vector? A vector is an object that has magnitude and direction. So an object that has a magnitude and a direction. Now, there's other rules to it, but from a conceptual physics standpoint, that's pretty much all you need to know. More advanced physics classes, they'd say there's ways that they transform. There's specific rules about how they must behave. You would recognize some of the rules as the rules that you learned when you first took pre-algebra. You know, A plus or A minus B is equal to A plus the opposite of B, or there exists a negative such that a plus the negative of a gives you zero, little stuff like that. But let's give some examples. Examples are force, which we normally indicate as an F with an arrow over it. We use the arrow when we're handwriting stuff. You can also use a slightly different version of an arrow. Some people will do this, and some people will do this. All of those are really acceptable. But another vector quantity is the velocity. So velocity is a vector quantity. Also acceleration and momentum. And momentum, oddly enough, is given by the symbol P, but it's given as a formula wise as the mass m times the velocity vector v. And it turns out when you multiply a scalar by a vector, if that scalar is a positive number, then you only affect its length, not its direction at all. If that number is positive and less than one, it'll make it smaller. If that number is positive and greater than one, it'll make it bigger. If it's negative, on the other hand, it's going to do the same stuff, except it's also going to turn it around backwards. So when we say P equals m times v, then we know P and v must be exactly parallel because mass cannot be negative. So there's some examples of vectors, and the most important one is the one that I use as a archetype to help you guys understand how you add vectors, and that particular one is called the displacement. Now, this is not really the same thing as displacement you might have learned from the Navy or the displacement of a ship or something like that. This is displacement, which is supposed to be represented by a vector that points from where an object was or where an object started off at to where the object ended up being. That is what the displacement vector is, and we often use a symbol like d or lowercase d like that. So just remember it's from where you start to where you end up. So that's really what this displacement vector is. Now, to contrast the displacement vector, which our archetypal one is the displacement vector, but the one that helps us remember what's the vector versus what's not the vector is the velocity, because velocity and vector both start with v. There's also a quantity called a scalar, and that scalar is a number, a number that has no associated direction. Okay, so numbers are like the number one, or -5, or -2.4, or pi, or something like that. Now, in some sense, you can think of on a number line, the number one, in some sense, could be represented by a arrow pointing from the origin to the number one on the right, and that is once you get to that point where you're talking about a line or an arrow that points from one place to another, you're actually moving into the way we represent vectors. So as another note to the what is a vector, we can actually consider a vector as being modeled perfectly by a drawn arrow. And what you do is you use a scale that is consistent. So, for instance, you'd say on the scale, 1 inch is equal to 25 newtons or something like that. And then you, of course, indicate the direction by using a protractor and maybe drawing some cardinal directions like east, north, south, and west. And then you could say things like the vector that points 15 degrees north of east, or the vector that points 30 degrees south of west, and stuff like that. So that's another version of what a vector is. It's a little arrow whose length is proportional to the length of the vector, and whose direction is in some sense parallel to the direction of the vector. Whereas a number, scalar, is just a number without any direction associated with it, but it can be a positive or negative number. And examples are speed, S, mass, we use the symbol M for, temperature, which we use the symbol T for, and time, which we use the symbol lowercase t for. Again, the archetypal one, or at least the one that we use as a mnemonic to help us, is the speed, which starts with an S, just like scalar does. So we've got speed starting with an S and it is a scalar. We've got velocity starting with a V, which is a vector. And we represent vectors by arrows whose length is proportional to the magnitude and whose direction is supposed to be parallel to the direction of the actual vector. So that's a little bit about that. How do we add vectors that are parallel? Well, what I've been hinting at here is the idea of the displacement vector being the archetype of helping us understand exactly what addition of vectors means. So let me start off by drawing a little rectangle that, let's say, represents a house. So this might be, for instance, your house. This, for instance, might be your front porch. And you could say you're standing right on the front porch right there initially. And actually, I need to draw that a little better. It did some crazy stuff because it was trying to guess what I wanted. So let's say we started there. If we started there, and let's say this is north, this is east, this is south, and this is west, then we might wish to, for instance, walk a little distance due north, at which case our displacement would be that vector, and I'm calling it D1 because my intent is to draw other displacements as well. So the first leg of my trip was given by displacement D1, which points from the original location I was at, which is the X on the front porch, and points to the location I ended up at at that particular point, so I'll just draw an X there. Now, if I chose to take a walk east, then I'd have another displacement vector that I'd probably call D2. And that's the second displacement vector. And that started from the second spot where I drew an X and ended on the third spot where I drew an X, which is right there. So if you think about those two as displacements, then you could say if we make the understanding or we reach the understanding that vector d1 plus vector d2 is the total displacement in going from point 0 to point 1 to point 2, which I could indicate like this. This is point 0, this is point 1, and this is point 2. Okay, so we'd say displacement from 0 to 2 is equal to d1, which goes from 0 to 1, plus d2, which goes from 1 to 2. That would be exactly it, in which case you could see that the displacement is this vector that points from point 0 to point 2. So this vector right here is the one we're calling D0, 2, and that is how vectors add. You can imagine the vectors put head to tail, head to tail, head to tail, and that actually results in the displacement. So notice what I did was I drew the first vector with its tail at point 0 and its head at point 1. And then I drew the second vector with its tail at point 1 and its head at point 2. And then I drew the displacement vector from point 0 to point 2 as from point 0 all the way to point 2, and that's our displacement vector. And basically, by the tail of vector d2 being at the head of vector d1, that means those two vectors were in head to tail formation. So d1 and D2 are in head to tail position. The sum is a vector from the original our first tail to the last head. The head of the vector is, of course, meaning the part that has the arrow, and the tail of the vector being the part of the arrow that has no head on it, no arrow on it. Okay, so that's one of them. But the most simplest case is what about when they're parallel? Well, that's easy enough. If I take a vector that is, let's say, 3 units long, let's say that is vector A, and then I walk from there a distance 2. Then that part is vector B. And from that, we can see that the vector from here to here is what we call the resultant R. And that's a fancy word for the sum of any number of vectors. In this case, it was just two vectors, but the resultant R, when they're parallel, just happens to be a length of exactly the sum of the two lengths. In other words, when the first vector was 3 units long and the second vector was 2 units long, they pointed in the same direction. So this vector, the resultant, has a length of 5, which is equal to 3 plus 2. And it points in the direction of both of them. So there's no ambiguity when you have two vectors that are parallel. They both point in a fixed direction, and that fixed direction is the same in both cases. So all you have to do is add the magnitudes of the two parallel vectors, and you'll get the magnitude of the resultant. If it was three vectors, you'd add the magnitudes of all three and then get the resultant. So that's the first part, but we've used that little idea of the displacement being displacement 1 plus displacement 2 plus displacement 3 plus displacement 4 is the total displacement as our model for addition. So hopefully that little house with the porch made some sense, and it'll help us make more sense when we get to vectors that aren't parallel. So let's go on to the next one. How do we add vectors that are anti-parallel? Anti-parallel means in the opposite direction. So again, we're going to use the idea of a walking trip, a displacement, to tell us what addition of vectors is. So let's imagine, for instance, that we walk a distance of 4. Let's make it 5 since I drew 5 instead. So we walked a distance of 5 units to the right. And then from that, we walked a distance of 2 units to the left. Those two vectors are anti-parallel. The A vector is the black one, and the B vector is the red one. Now, if you imagine walking a distance of 5, let's say 5 feet, but then you walked back a distance of 2 feet, then it'd be obvious that the distance you have left is 3 feet. So that's actually what displacement teaches us. If we walk to the right 5 units and then we walk to the left 2 units, we're now 3 units from where we started from, and the displacement, of course, would be 3 units to the right. So the resultant of these two vectors is, I'm going to use the color purple here, and that resultant is this vector. Resultant is equal to A plus B. So uh, in the case of parallel vectors, the sum of the lengths is the total length, and the direction that they both had is the total direction. Remember, a vector is supposed to have magnitude and direction. I just told you how to do the magnitude. You add the magnitude of one parallel to the other, and then you add the length of the second one that's parallel to the first one, and that gives you a new total. That's the total length of the sum of the two. And since the direction for each of those are both to the right in this case, then the total vector should point to the right. So you just add the two magnitudes when they're parallel, and you take the direction that either one had as the direction. When you have two that are anti-parallel, then what you have to do is figure out which one has the biggest magnitude. So for instance, in this case, A had the biggest magnitude, it was 5, but B had a smaller magnitude, so A plus B, since they're in opposite directions, they're actually going to subtract. And what you do is you take the big number, the one with the largest magnitude, and you subtract from it the one with the smallest magnitude. So in this case, I did 5 minus 3, and that gave you the magnitude. And the direction is the direction of the one with the largest magnitude. So the resultant magnitude is the largest magnitude minus the other, oops, smaller magnitude. So magnitude of R, which you normally write like this with the absolute value bars around it, but you could also just write it as R without the vector symbol. That's going to be 5 minus 2 equals 3. The direction is the direction of the vector with the largest magnitude. Okay, so again, vectors are objects with magnitude and direction, and I just told you how to get the magnitude and direction. For now, two vectors that are in opposite directions are anti-parallel. You take the vector that has the largest magnitude, and you take that magnitude and subtract from it the vectors with the smallest magnitude, and that gives you the resultant vector's magnitude, which in this case was 5 minus 2 equals 3. And then you recognize that the vector that had the magnitude of 5 was the larger one, and it pointed to the right, so it's going to win the sign war, or the direction war, if you will. Therefore, the actual vector is going to point to the right and have a magnitude of 3. Just in contrast to the two parallel vectors, the sum of the vector magnitudes is actually equal to it. So in this case, I wrote it down there, but just to let you know what that means R, the resultant magnitude, which we could also call R, is 3 plus 2. This one's the magnitude of A, and this one's the magnitude of B. And of course, that gave us the magnitude, and the direction was just the direction that they both had. In the case of anti-parallel, we have to decide which one's the biggest. That one tells us what direction it's going to be. Obviously, we had a vector whose magnitude was 5. We had a vector whose magnitude was 2. So the 5 is the bigger one. So we know that the direction is going to be to the right. Then we do 5 minus 3 gives us 2, or excuse me, 5 minus 2 gives us 3. So 3 is the magnitude and it points to the right. Now, how do we add vectors that are parallel, or excuse me, that are perpendicular to one another? I actually showed you that on the displacement example where we actually walked uh, north for some period. Let's do a similar one. Let's say I'm going to walk north 3 units, and now I'm going to walk east 4 units. 1, 2, 3, 4, like this. So the purple one might be vector A, and the red one might be vector B. And the way you could do this is, since they're head to tail, you just draw a vector from the tail of the first to the head of the last. That's exactly the way we did it when we were talking about walking from the front porch. So this vector is the resultant, and it's equal to A plus B. Now, since these two are perpendicular, we have the good fortune that we can actually find the magnitudes using the Pythagorean theorem. If they weren't perpendicular, we couldn't use the Pythagorean theorem, but we can here. So, and some teachers will actually require you to know how to use this Pythagorean theorem for conceptual physics. Some don't, but all of them sort of require you to be able to draw what the resultant of two vectors added are, whether they're perpendicular, parallel, anti-parallel, or at an acute angle to one another. So the Pythagorean theorem for right triangles, remember a right triangle is a triangle that has one 90-degree angle, which is indicated by this little square box right here. So that's an actual right triangle. And the two legs that are touching, the two parts of the triangle that are touching the right angle are what we call the legs. So A is a leg, B is a leg, and then their magnitudes are given by the Pythagorean theorem, which says that a squared plus b squared is equal. You would normally say c, that's the formula you normally use, but in this case, I'm teaching you all that the resultant vector is called r. So we'll say a squared plus b squared is equal to r squared. The hypotenuse is the long one, and you can tell it by it being the longest one, but you can also tell it by this right here looking like an arrow pointing to the hypotenuse. So this looks like an arrowhead pointing to the hypotenuse. By the way, if you're talking about angles, this angle right here would have this as an opposite side, and it would have this as an adjacent side. Notice the sides are the same thing as legs, and there's an opposite and adjacent for any given angle. If we were using this angle, on the other hand, this one would be opposite. And if we were using this angle, this one would be adjacent. So notice in both of those cases, the adjacent and the opposite are not the hypotenuse. That's important to know. And the hypotenuse is the thing that goes by itself on the opposite side of the two squares in Pythagorean theorem. So in this case, we could actually solve it. We'd say, since a was 3, we would say 3 squared. And we could assume that's 3 feet. That would be fine. Or we could say it's 3 meters. That would be fine as well. B had a magnitude of 4 feet or meters or whatever, so that's going to be 4 squared, and 3 squared is equal to 9 because it's 3 times 3, and 4 squared, which is 4 times 4, is 16. Therefore, you get 9 plus 16 is 25, but 25 has to be equal to r squared, so that tells us r is equal to the square root of r squared, which would be the square root of 25, which is equal to 5. So the magnitude of this one would actually be 5 feet or 5 meters or 5 inches, whatever we wanted to do. So that's what happens when you add two vectors that are perpendicular to each other. If we were fortunate enough to have two vectors that are that are perpendicular to each other and are also the same length, then we could do something like this. Let's say this is vector A, and it's 3 units long. This is vector B, and it's 3 units long. And those are units, but I'll go ahead and put them in as meters just because we need to get in the habit of making sure we think about not only a measurement but also its units. So when we actually have two equal length vectors perpendicular to each other, you can do the head to tail method, but you can also imagine them as if they were tail to tail. So for instance, this red vector is identical to B because the only thing that matters, as far as we know, is the magnitude and direction. So you can see that the magnitude of B, the red one, is exactly the same as the magnitude of B, the purple one. And you can see the direction of B is also parallel to the direction of the purple B. So the red B and the purple B are exactly the same. When two vectors are tail to tail, which is what I have with the purple A and the red B, then all I have to do is complete the parallelogram. So I make one side that's parallel to vector B, I make the other side that's parallel to vector A, and then I draw the vector sum from the common tail to the opposite diagonal, and that would be the resultant R. So in this case, R is equal to a squared plus b squared, which equals 3 squared plus 3 squared, which equals 2 times 9. Notice 3 squared is 9 and 3 squared is 9, so 2 3 squareds, meaning 3 squared plus 3 squared is the same thing as 2 times 9. Now, that was r squared, by the way, not r. So now we have r squared is equal to 2 times 9. If we tried to solve this, what we'd have to do is take the square root of both sides, And when we take the square root of both sides, the right hand or the left hand side becomes just r. And we could technically do plus or minus, but lengths are never negative. Neither are magnitudes of vectors, but the components of vectors can be positive and negative. That's important to know if you go further on, but not too relevant to the conceptual physics. But when you take the square root of 2 times 9, you get the square root of 2 times the square root of 9. And of course, the square root of 9 is just 3. So we get the square root of 2 times 3. So r is equal to approximately 1.41, because that's approximately square root of 2 times 3 meters. And of course, you could fill that out by recognizing that 3 times 1.41 is actually 4.23. So that's going to be the case no matter what. If your vectors are perpendicular and equal in size, one's 1 and the other one's 1, for instance, then the resultant vector will be the square root of 2 times 1. If they're one's 2 and the other one's 2, it'll be the square root of 2 times 2. If one vector's 8.7 and the other vector's 8.7 and they're perpendicular, then it's going to be square root of 2 times 8.7. So there's two ways we can add vectors that are perpendicular. One, you can have them in the head to tail method. So this right here, oops, that was supposed to be in green, so it stood out. This one right here is the head to tail method. And this one right here is the parallelogram method. So completing the parallelogram, if they're tail to tail, and going from the initial tail to the last head, if they're head to tail. That's the way you add them. How do we add vectors that make acute, less than 90-degree apart angles with one another? Well, that's pretty straightforward as well, especially if we took it as a displacement. If we did it as a displacement, then we'd have to do the head to tail method. So that's certainly reasonable. So let me show you one of those. We could, for instance, go here, and that would be vector A. And then at the head of vector A, we could draw vector B. And vector B might be, let's say, this vector. Since they're head to tail, we know that the sum would just be from the tail of the first to the head of the last. So this vector right here is R is equal to A plus B. Now that one's kind of hard to see because I made them nearly parallel to each other, but they're not parallel. They are actually at an acute angle. I would say probably the angle is on the order of uh, only like 30 degrees or something like that, not very big. As another example, we could do something pretty significant like this angle for vector A and this angle for vector B. And again, the sum would be from the tail of the first to the head of the last. So that's it when they're head to tail. But what if someone gave you the vectors when they were tail to tail? So if, for instance, we had vector A this direction and we had vector B as this direction, then all we have to do is draw a vector parallel to A. So notice A went to the right one and up 3, so I expect it to come right here. So that's the parallel of A. In fact, I could even call it A like that. That's really what's going on there. Now I'm going to draw another one parallel to B. Oops, I never labeled B. Let's do that. Now I can draw another one labeled B. Now notice B goes down 1 and to the right 3, so I'm going to go down 1 and to the right 3. That should put me right there. So this vector is actually B. But now we've completed what's called the parallelogram. So the resultant goes from the common tail across to the diagonally opposite vertex, if you will, and that is R is equal to A plus B. Now, if you were taking a class that was more mathematical, you would learn how to use trigonometry and figure out what these angles are and everything. But you don't really have to do that to be able to figure out really what vectors are. You just need to draw scale drawings. And for instance, if you're using something like AutoCAD, AutoCAD is going to give you exactly the right answer instead of just an approximation. But if you're just doing it with drafting techniques, using a protractor, a straight edge, and a good ruler, and you're using a good consistent scale that you've designed so that it takes up as much paper as possible, because the bigger the diagram is, the harder it is to make a significantly large error. So if you try to add in two vectors and you take up the whole page, you're sort of maximizing your ability to not make a mistake. You're actually maximizing your efficiency. But you can just draw them scale to scale. So a scale like 1 inch on the paper is equal to 1 Newton in real life. And then you use protractors and you maybe draw a north, south, east, and west quadrant so you can figure out which way's east, which way's north, which way's south, which way's west. And then you could draw the vectors accordingly. And all you'd have to do is measure the resultant by using these head to tail or tail to tail methods. Draw the resultant, measure it, and then use your scale backwards to convert that number of inches to a certain number of newtons, and then use your protractor to measure what angle that makes, say, with due east, or what angle that makes with due north, or what angle that makes with due west or due south, or something like that, and then specify it accordingly. For the record, let me just give you what some of these vector directions mean. So if I drew a uh, compass set up like this, where I said this was north and this was east and this is south and this is west. This right here could be 15 degrees, and that vector would be called 15 degrees north of east. But it could also be called, since the total angle between east and north is 90, if I subtracted 15 from that, that would give me 75. So we could also say it's 75 degrees east of north. That's also acceptable, and that's specifically because this angle right here would have to be 75 degrees. Similarly, we could draw a vector, let's say right here, and let's say this angle, which I'm assuming all these go right back to the origin. Let's say this angle is 20 degrees, then this vector would be at 20 degrees west of south, or it could be also called 70 degrees south of west. So that's some typical definitions of what we call certain directions. I could go a little further and just tell you from a compass heading standpoint what these directions would be. So if we again imagine this is a compass, this would be the eastern direction, this would be the northern direction, this would be the southern direction, and this would be the western direction, like this. Then this vector would be at compass heading, and I actually meant to draw that in a different color, so let me see if I can draw it now. This vector would be at 0 degrees because we consider 0 degrees due north. This vector would be at 90 degrees because we consider 90 degrees due east. This vector would be at 180 degrees because east 180 degrees is due south. And then finally, this vector would be at 270 degrees, because 270 degrees uh, is considered due west. Those are the two compass heading type angles. I should also mention that in practice, you might also use the mathematically defined directions, which are based on the x and y axes. And in that case, this would be x, this would be y, and there's a couple ways you could measure a vector's angle. If your vector was like this, for instance, you'd measure counterclockwise from the positive x-axis, and you would call that, let's say, the angle A, and that angle would be, let's say, this one actually looks like it's really close to 45 degrees. If I went perfectly diagonal from corner to corner on these rectangles, that would be exactly 45 degrees, and this one almost hit that, so I'm just gonna pretend like it did hit it, and then we'd say A is 45 degrees. That's what it is when you measure it counterclockwise from the positive x-axis. Okay. If, however, you measured it clockwise from the positive x-axis, then this would be A is equal to, in this case, it's a negative number, and it would be 360 minus 45, which would be negative 315 degrees. So that's another way you can actually specify directions is mathematically, we just call the angle 45 degrees if it was 45 degrees counterclockwise from the positive x-axis. And if it was negative 45 degrees, it would be, for instance, in this case, notice I went straight across the diagonal here. In this case, the angle B would be equal to negative 45 degrees, and the negative is there because we measured it clockwise. Implies clockwise from the positive x. Okay, so I hope that helps you better understand how to add vectors. I would tell you, well, I'll go ahead and show it to you anyways, just for the record. If you want to add vectors, we've already handled all those cases. But if you actually wanted to subtract vectors, you could have two vectors that are, for instance, tail to head to tail, which might be like this, and this would be A, and this would be B. And if you wanted to know A minus B, turns out that rule that we learned in pre-algebra was correct, and super helpful now. It's A plus the opposite of B. And we've already mentioned that when you multiply a vector times a scalar number, if the number is negative, you turn it around 180 degrees. So in this case, A plus the negative of B means that now I just take B and I turn it backwards. Now, this is two vectors that are head to head, and we never learned anything about that, but we did learn things about when vectors are head to tail or tail to tail. So I could either move this vector so that the purple negative b is either head to head, or excuse me, head to tail with A, or I could put it where they're tail to tail with A. I'm going to put it as if they're head to tail by drawing B down below. Notice I have to go down one or down three and over to the left one to match what the other thing was. So, or what the vector on the left hand side was. So I can basically go down and over one, in which case this is negative B. Now I have negative B and A in head to tail formation, and all I have to do is, according to this rule, to subtract, I just add A and the negative of B. So, lo and behold, this is, let's say, D for difference equals A minus B, which was defined to be A plus the negative are opposite of B. So that's one way. Notice that was when they were head to tail. What if I had those same two vectors and they were tail to tail? In this case, it would actually be quite a bit easier when they're tail to tail. So this is vector A again. And now let's say vector B is going to be horizontal, and I'm going to try to make it about the same length as it was last time. Might be a little different. That's okay. So that's A and B. If we wanted to know A plus B, we would draw a completion of the parallelogram. But since we're wanting to do A minus B, I have to take B and turn it around backwards. So when I turned B around backwards, it became that purple vector, and now that purple vector is head to tail in head to tail formation with the A vector. So I just have to draw again from the tail of the first to the head of the last, which in this case becomes this vector right here, which again is D, which is A minus B, which is defined to be A plus the opposite of B. So that wasn't one that you're probably going to need to use in your conceptual physics class. You might have a reason to think about it though, so I thought I'd go ahead and give it to you. This is how you subtract vectors. At least graphically. Again, if you did all this to scale or use an AutoCAD, it would give you exactly the right results. Otherwise, you'd have to learn some math and do some trigonometry and geometry and stuff like that. I hope this helps, and I hope you now have a better understanding of how to add vectors. Bye bye.